Hi everyone, I wanted to work a problem from work session 17, question 9. The question states to calculate the molar solubility of magnesium hydroxide in a solution buffered at pH 10. How does this compare to the molar solubility of magnesium hydroxide in pure water? Alright, so I wanted to do the calculation in pure water first. Remember, when you do solubility product, you write the insoluble salt on the left side. So we have magnesium hydroxide as the insoluble solid. It's an equilibria because it can dissociate to a small extent. So I always like to write the cation first, magnesium, and then the anion, hydroxide. And then to remember that I need to balance this equation, so put the 2 out in front. And so it dissociates into magnesium cations and hydroxide anions. Now because we're in equilibria, we're going to do a rice table. And don't forget that solids are never included in the rice table. And in pure water, we can assume negligible amounts of the magnesium and the hydroxide. And then as you do any rice table we've done before with other applications like the weak acids and weak bases, products, you're going to say plus X, but don't forget here it's plus 2X. A lot of times when we do the acid bases, everything's 1 to 1. And so students fall into the habit of saying minus X and plus X, but don't forget, especially for solubility, that there are stoichiometric coefficients and you'll want to include that. So in this case, plus 2X. And so at equilibrium, it'll be 0 plus X, which is X, 0 plus 2X, which is 2X. And the KSP is something you can look up in the back of your textbook. All the literature constants back there. If you're taking one of my assessments, it'd be provided for you. For this magnesium hydroxide, it's 2.06 times 10 to the negative 13th. And that's equal to the concentration of products over reactants, but we don't include the reactants here because they're solids. Don't forget to put that squared up top there. And so this is equal to X times 2X squared. And so this is equal to 4X cubed. And so X, when you solve for it, you would want to divide 2.06 times 10 to the negative 13th by 4, and then take the cubed root of that answer, and you should get X is equal to 3.72 times 10 to the negative 5th molar. So anytime we talk about molar solubility, what I always tell my students is just to solve for X. Basically, it's to what extent that this insoluble solid can dissolve. So if I make a solution that is 3.72 times 10 to the negative 5th molar or more dilute, then I won't see a precipitate come out because it will dissolve to that extent. If I make anything more concentrated, let's say like 2 times 10 to the negative 4th, then yes, I will see a precipitate come out of solution for magnesium hydroxide at 25 degrees Celsius in pure water. So this gives us an idea of to what extent it will be soluble. We always say just solve for X because when we write these reactions, everything is written to normalize the insoluble solid to 1 for the stoichiometric coefficient. So that's why you're always kind of solving for X to see at what extent did it actually dissolve. Okay. If you were to do 2X, then that doesn't match the stoichiometry for the solid. All right, the next part of this problem was asking about, well, what happens if you're working with a buffer of pH 10? Now, the first thing you want to recognize here is that pH 10, is this acidic or basic? It's technically more basic, right? So there's more what in solution? More hydroxide ions, good. So let's go ahead. When we think pH 10, we know pH is equal to negative log of the hydronium ion concentration. And so in that case here, to find the hydronium ion concentration, that would be 10, the antilog, 10 to the negative pH. And so when I plug that in, I got 1 times 10 to the negative 10th molar. Now you could have gone pH to POH to get the hydroxide ion concentration. Either way, it works. I have the hydronium ion, and I remember that the hydronium ion, or Kw, is equal to the hydronium ion concentration times the hydroxide ion concentration. A good number to remember, Kw is 1 times 10 to the negative 14th at 25 degrees Celsius. So you can always figure out, if you have one concentration, then you can figure out the other. With that being said, that means the hydroxide, if I take 1 times 10 to the negative 14th and I divide by 1 times 10 to the negative 10th, my hydroxide ion concentration is 1 times 10 to the negative 4th molar. And so I come back to my race table here. I'm going to include that concentration up at the top. We're initially starting with this buffered system, so the concentration is a little bit more significant than it would have been in pure water. You know, in pure water, it's about 1 times 10 to the negative 7th, and so typically we don't include that number up here. We just say 0. But now we're getting something a little bit more concentrated, so you would want to include that and see how it affects the molar solubility. Follow the same pattern here. This is plus 2x. A lot of times students forget the 2. That's why I keep emphasizing that. So 1 times 10 to the negative 4th plus 2x. And then KSP is equal to the magnesium concentration. We're going to use the same expression here and plug it in. So magnesium times hydroxide squared. So then you would have x. And then 1 times 10 to the negative 4th. Plus 2x squared. Now, if you're taking my class, we're going to assume x is small enough to ignore and save you the trouble from doing the math here. And it'll still give you a good estimation. Since KSP is really tiny anyways, the x isn't changing all too much. And when you do solve for x in this case, you should get, because you're setting it equal to 2.06 times 10 to the negative 13. Then when you solve for x, you should get 2.06 times 10 to the negative 5th molar. So what does this mean, right? Like I always like to tie it back into theory. So we learned in our online lectures about the common ion effect. And when you're working in a buffered solution, in this case here, when we are working in a basic solution, we had a higher concentration of hydroxide ion. So the common ion here is hydroxide in this case. And when we increase the concentration of the hydroxide ions, how does that shift the equilibrium based on Le Chatelier's principle? It should shift it to the left. Right? And so in this case here, we would expect the molar solubility to be lower than it would be in pure water. And that's all due to the common ion effect. We increase the hydroxide ion concentration by working in a buffered system of 10, a more basic solution, and therefore shifted the equilibrium to the left, making more of the insoluble solid. So we would expect it to be less soluble at pH 10 than it is in pure water. Alright, I hope you found this video helpful. If you have any more questions, do not hesitate to send me an email.